All right, in this video, we'll look at the answers and point values for AP Practice Problem E. AP Practice Problem E has a lot of implicit differentiation in it. And if you recall, implicit differentiation is used when you can't get one variable alone or you don't want to. You can basically take derivatives of multiple variables so long as you use the chain rule. You basically pop out a dy dx or something like that. All right, so in the first problem, or let's just look at the main problem, I guess, they give us this curve, 2x squared plus 3y squared minus 4xy equals 36. This is not actually a function, it's a relation, so we're not able to actually get y by itself. They do want us to still show, though, what the derivative is, that dy dx, the derivative with respect to x, is this expression. And we can tell it's implicit because it has y's and x's in it, where a regular derivative just has the one variable. This needs both variables to be expressed. So to do this by implicit differentiation, I want dy dx, so I'm taking the derivative with respect to x. And to do that, I need to do that on both sides and find the derivative of each piece. Anything that has an x in it, so I'm taking it with respect to x, you can just write the answer. The derivative of 2x squared is 4x. Anything that doesn't have the x in it needs to have the chain rule used, because you're going to take the derivative of this, which 3y squared's derivative is 6y, but then because the y is a different variable than the x, y is basically a function of x, and this is like a function inside a function, so you need to do the chain rule to it. Now, we don't know what the inner function is, because we don't know what y is, but whatever it is, we can call it dy dx. So this pops out, and this is actually what you want, because you're trying to find, or trying to verify that this is actually the derivative. So we want these dy dx's to come out because we want to solve for them. If I continue, minus 4xy, now this is more difficult to get because it's a product rule. X and y are different functions or different variables. So I'm going to have to do the product rule to it. So I left the negative. You could keep the 4 with the x or separate it. I separated the negative 4 by itself and then just took the derivative of x times y. Since this is multiplied, use the product rule. The derivative of the first is 1. Remember, respect to x, so we can leave it. Leave the second, add the first, and then when we do the derivative of the second, y's derivative is 1, but since it doesn't match the variable, we need dy dx put on it, put on the 1. So I didn't write the 1, but that's the derivative. So that side's done. What's the derivative of a number? Well, derivative of a constant, or just a plain old number, is always 0. So now I've taken the derivative with respect to x. So this has had implicit differentiation done to it, but they want me to verify that dy dx by itself is this thing. So the rest of it's using algebra to get by itself. So I believe there was 1 point for doing this product rule in general, or this general derivative, and then going through to get the dy dx by itself so I can do the verification. Well, 4x is fine, 6y dy dx is fine so far. This negative 4 needs to be distributed in, so I get negative 4y and then minus 4x dy dx. Now, the goal here is I want to get dy dx by itself, so I'm going to move the terms that don't have dy dx over to the other side. So I'm going to subtract the 4x over and add the 4y over. There they are. And then from here, the dy dx's are alone on this side. Since they share the dy dx, you can basically factor it out. So this dy dx that they both have pops out, and I get dy dx times 6y minus 4x. And since these are being multiplied now, this can be divided over. So it divides, you get this fraction, and this is basically that solution, because there's you can basically take a factor 2 out of each of these and cancel. So if you divide 2 out of every term, you get 2, 2, 3, and 2, which is exactly what they found. So this verification gets you the second point, all right? So this basically says, yeah, if I take the derivative of this, I get this expression. Part B wants us to find the slope of the tangent line to the curve at each point on the curve where x is 6. So one of the hints is it says each point. Remember, I said this wasn't a function, meaning that an x value can have more than one y value. In this case, if you see the work, we're going to get 2 y values. So the first thing you need to do is find where those y values are, because they don't want the tangent line equation, but they want the slope of the tangent line, which is essentially just the derivative at the spot. So I need the derivative at x equals 6, but I can't get it right now, well, until I do the work, because x equals 6, I could plug into the derivative, but I need to know y. So the way I'm going to do that is take x equals 6 and plug it into the original equation. So 6 goes in for x. That leaves you with just y's, and now you can solve for y. So the way I solve for y is, well, first I got these numbers. So this part was 72, and this part became minus 24. So now I have y squared and y. This is a quadratic equation in variable y. So the way we solve a quadratic is to get equal to 0 and, if possible, factor. So I moved over this 36 and rearranged the terms. I now have the quadratic 3y squared minus 24y plus 36. I divide the 3 out, because if you divide both sides by 3, no harm done. And then it makes the numbers easier. It actually makes this easier to factor. And now this thing factors into minus y minus 6, y minus 2. And if both of those equal to 0, well, then your solutions are y equals 6 and y equals 2. So basically on this function, whatever this curve looks like, you can basically, if you were to go to 6, you'd find that there'd be a point at y equals 6 and a point at y equals 2. So both of these are spots on the curve, and we want to know what their derivatives are, what their slopes are, right? If we were to make the tangent line, what would the slope be? Well, the derivative will tell us that. The derivative needed both x and y, but I now have what x is and what y is at each one of those spots. So I'm going to evaluate, to get the slope, I'm going to get the derivative at the point 6, 6. To do that, just plug in 6 and 6, because the x's are 6 and the y's are 6 in that derivative. So that comes out as 0 over 6, which is 0. And then if you do that in the second one, the 2's are now y, because of the 0.62. That's the second one I found. The y's are now 2. The x's are still 6. That comes out as 4/3. So there's 1 point for each slope. Unfortunately, this is a lot of work, but since it's all pre-calculus kind of work, they don't actually give you any points for it. You need to get to here in order to start earning the points. So the calculus part is knowing how to use the derivative, and that's what gets you the score or the point for each one of those. All right. Part C asks a pretty good concept question about slopes, because it wants the positive value of x at which this curve has a vertical tangent line, and wants me to show the work that leads to the answer. So in order to have a vertical tangent, vertical lines, you have to go back to algebra and realize vertical lines have undefined slopes. A vertical line goes up a certain number, like it might go up 3 or go up 5, or essentially goes up forever, and goes over 0. So when you go like up 3 over 0, 3 over 0 is undefined. It's like an infinite quantity, but infinity is not a number, and it's finicky. So basically we say it's undefined. So what you have to know is, if they want a vertical tangent line, they want the tangent line to go straight up and down. In order for that to happen, the tangent line will be vertical when the slope, aka the derivative, is undefined. When is the derivative undefined? Remember, this thing in the beginning is the derivative. A fraction's undefined when the bottom's equal to 0. So that's what I put, that the tangent line's vertical when the derivative is undefined, and that happens when the denominator equals 0. Now, the problem with solving this is you can't get a value right now, because if you set the bottom equal to 0, the best you can do is solve for one of the variables, because it's a two-variable equation, and you don't have two equations yet to solve with it. So if you solve at least for one of them, I got the y alone, because they're looking for x. If you get y alone, y has to be 2x over 3, or 2/3 x. What you can do with this, though, is if you had another equation, basically if you want to solve two variables, you need two equations. Well, I have this equation already solved out. I can substitute this in back to the original equation. So if I substitute this in and get the y's out of there and replace them with that expression, it'll all be x's, and I'll be able to solve for it. So that's exactly what I did over here. I'm going to find x by substitution. I threw y. Everywhere I saw y, I threw in 2x over 3. And that means here I had to square y, and here I had to just put a regular y. Now you go through and simplify all this. That got me down to a bunch of x squared. So this term was 4x squared over 3. This one was 8x squared over 3. This one was 2x squared, but I decided to put it over 3 as well to basically get a common denominator here. 6 over 3 is 2. So now they're all fractions of x squared, and since they're all like terms, I can combine them. So I have 6x squared over 3 plus 4x squared over 3. That's 10x squared over 3. Then subtract 8x squared over 3 leaves me 2x squared over 3. So now from here, you just got to get rid of this fraction. You can multiply by the reciprocal. 2x squared over 3, well, you got 2 over 3 multiplied by 3 over 2. 36 times 3 over 2 is 108. I did in 2 steps. Multiply the 3, divide the 2. I think I'm showing it on the key to make it easier. But if you did in 1 step, multiply by the reciprocal, you get 54. Either way, go through, get x squared is 54. Square root, you do have to do plus or minus. So there are 2 solutions, plus or minus radical 54. But they are clear in the directions. They do say get the positive value. So you don't want to report the negative radical 54 as an answer. The positive value is square root of 54. All right. And if I don't miss my mark on this, I believe this thing is an ellipse. Not that you really need to know that, but if you think about it's got an elliptical shape, it would make sense that it would have, for like x equals 6, it would have 2 values. It would also make sense that it's got 2 vertical asymptotes because the ends of the ellipse would do that. So like I said, I'm pretty sure that's an ellipse just from the structure of it. It's got positive x squared, positive y squared. And so it makes sense to get 2 solutions, just give them the positive one. So square root 54, that can be simplified, but remember you don't have to simplify. All right. The last one is to do some more implicit differentiation. They give you the equation, again, the same one from the top, and basically say that now they're relating them by time. T is not in the equation, but you could still take the derivative with respect to t, even though there's no t variable in there. How is x and y changing with time? That's a question of doing the derivative with respect to t. They want at t equals 1, give us a whole bunch of other values, that x is 6 and y is negative 2. Dy dt is 4, and then wants to find dx dt. So basically, if I do the same thing I did in part A, just take the derivative of the equation, but now do it with respect to t. Now, every time you take a derivative, the variables don't match, so everything needs to spit out that chain rule. So 2x squared's derivative is 4x, but I have to put the dx dt because the variables don't match, so that's the chain rule part. X is a function of t. I don't know what it is, but I know that's that's the inner derivative as a symbol. This thing is 6y. Once again, the variables doesn't match, so I have to spit out the dy dt. And then this thing's got to have that product rule done again. So I took the negative 4. I basically treated the negative 4 by itself because it's a constant, then did the product rule with these. The derivative of x is 1 dx dt times y plus x derivative of y is 1 dy dt. So it spits out all these dx and dy dt's, and then the numbers derivative is 0. This is the expression for the derivative with respect to t of all those variables. So like last time, I'm going to distribute this, and basically you get a point if you recognize you need to do the product rule. So I earned a point just by doing this. Distribute this negative 4, so you get negative 4y dx dt and negative 4x dy dt. And this thing now, they give you all the values, because what happens at t equals 1? Well, I want the derivative. I want this thing at t equals 1. Now, I don't have any t's in here, but I know all the other values. When t is 1, x is also 6. So everywhere I see an x, I'm going to plug in a 6. Y is negative 2, so everywhere I see a y, I'm going to put in negative 2. And dy dt, because now there's not only x's and y's in here, but there's dy dt's and dx dt's. They tell me dy dt is 4. So with all that information, so here's dy dt in 2 spots. When I plug everything in, I get all numbers except for the unknown dx dt, which is what I'm trying to find. So from here, I just simplified everything. I get 24 dx dt. Here I get plus 8 dx dt. These just are numbers, minus 48, minus 96. So now I just need to solve for dx dt. I combine the numbers and combine those dx dt's. I got 24 of those, dx dt values, 8 of those dx dt values. Put them together, I get 32 of them together. So now solve this equation, add the 144 over, divide the 32. Now dx dt is by itself, and it has to be the quantity. 4.5, or as a fraction, you could put 9 halves, or you could even leave it 144 over 32 if you wanted to. So there's a point where you get a point for getting down to this derivative. So if you had the product rule but nothing else correct, you'd get the 1 point. Having this properly done is the second point, and then that answer gives you the third point. All right, so this had a lot to do with slopes and implicit differentiation. So hopefully this helps in case they normally ask something about this, because basically implicit differentiation is one of the major forms of being able to take a derivative. Basically, you use regular derivatives if you got one variable. If you got multiple variables, you need to know this process of implicit differentiation. And unfortunately, in this problem, they normally don't test the same concept over and over again, but Part D and Part A are essentially the same kind of problem. It's just this one is with respect to x, which is a little easier, and they also gave you the answer, where here this one's respect to t, which is a little more difficult because you get more of these unknown derivatives. But really, once you get the derivative, it's just plug and chug. All right, well, hopefully this helped out, and then in the next video, we'll look at practice problem F.